States of matter and STP. Okay, STP refers to standard temperature and pressure. These are conditions under which we carry out different chemical reactions. The reason that we have a standard temperature and pressure is so that people in China could carry out a chemical reaction, an experiment, and publish their results. Say they were done, everything was conducted at STP. Someone in America can perform the same trial, the same experiment, know the conditions at STP, replicate that experiment, and then either confirm or contradict it. But again, the fact that both experiments were conducted under standard conditions, the same conditions, means the results can be compared. Standard pressure is, they give you the units kilopascals and ATM, the two different units, atmospheric pressures. We'll talk more about these later when we deal with gases. The only time we're concerned really with pressure is when we're dealing with the chemistry of gases. And then standard temperature is 273 Kelvin or 0 degrees Celsius. They are the same thing. They're equivalents. We'll convert back and forth between them later. We'll find the Kelvin scale we'll use when we're dealing with pressures and gases, because when we do these PV equals nRT, sounds pretty interesting, I'm sure. The T will do calculations where this will end up in the denominator, and we can't have the denominator be 0. So that's why the two scales exist. I won't get into it much more than that because we're going to go a lot more in depth later on when we deal with gases. Three phases that we are concerned with in reagents chemistry are solids, liquids, and gases. And I'm sure you're familiar with them in a general sense. We'll talk about these, which elements are solids at STP. When you look at the periodic table I have in my room with all the pictures, it's easier to see. You will have to be familiar with where you find the majority of the solids at STP, and most of them are the metals and metalloids on or below the staircase, and there are a handful that are above the staircase. Carbon, graphite, or diamond is one of them. And there are, again, we talked about keying the periodic table for different things. We can key the periodic table for solids, liquids, and gases, at least the majority, also, as well as we can for metals, nonmetals, and metalloids. The liquids, only 2 elements are liquids at STP. They are bromine and mercury. One metal and one nonmetal. I know when I was a kid in high school, we used to get to play with mercury, and probably wasn't the safest thing in the world. And if a mercury thermometer broke, we actually cleaned it up with paper, pushing the little beads around on a carpet. They don't really do that anymore. But remind me in class, and I'll show you. We've got a little container we keep in a safe place. Mercury is an incredibly heavy, dense liquid, and it's used still today in dentistry, somewhat controversially, for making amalgam fillings because it makes the metal so malleable. It takes shape a lot more easily when you mix it with a tiny bit of mercury. Keep that in mind when you go to the dentist. It's more motivation not to eat too much sugar. And one thing I didn't mention here, we'll always talk about the solids, liquids, and gases in terms of volume and shape. Solids have a definite volume and a definite shape, which means they are consistent. They stay at the same volume. They stay at the same shape, no matter whether you put them in different containers of different sizes. If I had an ice cube and put it into a glass, it won't fill the glass. The ice cube won't take the shape of the glass. And that's why we say it has definite volume and definite shape. It stays a cube until it melts, which takes us to liquids. Liquids have a definite volume, which means if I take an ice cube and put it into a glass and over time it melts, it won't fill the glass unless it's a really big ice cube. But it will take the shape of the container. Okay, the ice cube doesn't take the shape of a container. It stays the shape it was when you put it in there as long as it's a solid. Once it melts, you'll see it fill sort of the bottom of the glass and then round up the edges. And if you were to turn that glass on its side, the now liquid water would conform or take the shape of the container, but it won't fill the container. Which brings us to gases, which now have no definite volume. Means the volume changes based on the volume of the container. That is sort of answered here, or confirmed here, where we say that when it comes to shape, they don't just take the shape of the container, they fill their container. So if I had 1 liter of a gas and transferred it to a 2-liter container, I would now have 2 liters of that gas. Same number of particles, but because they're gases, they'll fill whatever container they're in. So if you change the volume of the container, the gas will fill that new volume. And then these are particle diagrams for the 3 different phases. What you see here, and you'll see this on the Regents exam, solids have what's referred to as a regular geometric pattern. You'll also hear the term crystal or crystalline structure. When you see any of this, you're talking about solids. A regular geometric pattern or a crystal structure. It's rigid. You can see these rows are very straight. So are the columns. The indication from this particle diagram is that nothing's moving and nothing ends up overlapping. Here you can see how the particles overlap one another. That's to indicate in the diagram that these particles are now mobile. Okay, and we would say as far as solids are allowed to vibrate about fixed points or a fixed point. Liquids, we would say, are now moving, so they vibrate about moving points. An analogy I use all the time, when solids vibrate, you hit them, sound waves run through them. The particles can move from side to side. They wiggle back and forth and sort of shake like a 7th grader at a high school dance. They don't really go anywhere. They just kind of wiggle in place and stand there, and they move around a tiny bit, but they pretty much their feet stay firmly planted in the ground. When you get to liquids, it's more like square dancing. The particles don't move apart from one another. They're always linked. For square dance, you lock arms with partners and move around. The people never move apart from one another. So they're moving more. They're moving around instead of moving in place. So that's what we'd say, moving in place versus moving around. And then when we get to gases, a lot of times you'll see they'll put these little tails on the particles to indicate they're moving very quickly. And for gases, we say they have the highest freedom of movement, the greatest range of movement, and they are now moving more freely than any other phase. We just kind of leave it at that. We don't talk about them vibrating, about moving points. We just say particles move freely. And for that one, the analogy holds. I've always used it's like hippies on Red Bull in bumper cars in a Walmart parking lot. really fast bumper cars in a Walmart parking lot. I like the visual. Lots of space. They move around randomly fast, straight lines, and they bounce off one another, redirect, and continue moving really fast, randomly in straight lines. And they're as spaced apart, as far apart, and as freely moving as can be.